This is problem 25 of chapter 15 of the textbook Stats Modeling the World by the authors B, V, and D. Okay, so there's lots of ways of answering this problem. We've worked on different ways of looking at independence, but basically what they're asking us here is if you draw a card from a well-shuffled deck, is getting an ace independent of suit? So remember, a suit could be a spade, club, heart, or diamond. So let's just recall that one way, if we use the probability computation stuff to answer this question, is we could ask, what's the probability of A given B? And is that equal to the probability of A? We can ask that question. And if yes, then that means that this condition B doesn't really change the probability of A. So if yes, that implies they're independent. And if no, it implies that they're not independent. So you can kind of just try something. So let's just try something. Let's ask, what's the probability of getting an ace given it's a club? Okay, and then we could ask, is that equal to the probability of an ace? And we'll just test it. So the probability of an ace, so there's 4 aces. There's 1 in each suit. So there's 4 aces, 4 out of 52. So now, if it's a club, so we have to kind of go over here. The probability of an ace, given that it's a club, well, that's the probability of an ace and a club divided by the probability of a club. So the probability of a club is 13 out of 52 because there's 13 clubs. And the probability of an ace and a club is only 1 out of 52. So if I simplify that, that's 1/3. So 1 out of 13. Okay, so is 1 out of 13 equal to 4? So let's see, if we factor 4 out, 4 times 1 and 4 times 13. I believe 4 times 13. What's 4 times 3? 12, 1. Yeah, 52. So 4 times 13. So the 4's cancel. So 13 equals 13. So it looks like it works. So that it's yes. So this suggests independence. But just to be thorough, let's switch it around. Let's ask, what's the probability of a club given it's an ace? Is that equal to the probability of a club? And you could have chosen heart or diamond or whatever suit. So the probability of a club is 13 out of 52. We know that. Okay, so now what's the probability of a club given it's an ace? So that's equal to the probability of both divided by the probability of the given. If you've watched these videos, have you noticed that I bounce back and forth by writing out and both? I'm trying to model both, doing it both ways, so you can choose which one you like. So the probability that it's an ace and a club, we already did that. It's 1 out of 52. And the probability of the given is an ace. The probability of an ace is 4 out of 52. So if we do the math, 1 out of 52 times, we flip this, 52 out of 4, we get 1/4. Okay, so we can put 1/4 over here. So 1/4 equals, if we factor out 13, 13 times 1, and to get 52, 13 times 4, right? We did that above. So they cancel, and you get 1/4 equals 1/4. Okay? So since the probability of a club given an ace equals the probability of a club, and the probability of an ace given a club is equal to the probability of an ace, they are not, or they are independent. Sorry about that, but we can always go back up if we get a little confused. Yes, so they're independent. Okay, so that's how you do that problem. That's one way to do that problem. There's other ways to justify it. Good luck.